Awesome.
Yes.
Thanks very much. And I really want to thank the organizers for giving me the opportunity to chat with you today. And I really want to thank the organizers for uploading all the talks onto YouTube, which due to time zone constraints, I have found particularly useful. So yeah, I want to talk to you today about some work that my collaborators and I have been doing studying the evolution of cold accretion flows that accrete onto massive galaxies and protoclusters at high redshift from the cosmic web. This work is basically a summary of several papers over the last few years that are listed below. And to kind of jump right in, we all know that galaxies form in the cosmic web, and this is an example of a cosmological simulation of kind of a proto-cluster environment. This is a snapshot at redshift 4, and you can see on the right-hand side kind of a configuration of 3 pretty massive galaxies. Each of these has a halo mass of a few times 10 to the 12 at redshift 4, and all the smaller black circles represent kind of, lower mass galaxies that reside inside individual cosmic web filaments, whereas the 3 most massive components of the protocluster are fed by individual filaments that are much narrower than the size of their virial scale. And the thinking is that these filaments are able to funnel gas from the cosmic web directly into the centers of these galaxies, and thereby, even when you have very massive dark matter halos that have halo masses of a few times 10 to the 12, 10 to the 13 solar masses, where we know that we expect the circumgalactic medium to be very hot. We heard a lot about this kind of a very hot intracluster medium or circumgalactic medium. The thinking is that since these intergalactic filaments, or cold streams as they're called, are so much narrower and so much denser than the typical densities in the circumgalactic medium, their cooling times are much shorter than the ambient cooling times in the hot halo, and therefore they don't shock heat, but they basically free fall cold at 10 to the 4 Kelvin directly toward the center of the galaxy, and are able to thus sustain observed star formation rates of 100 solar masses per year in some of these cases, and result in a lot of observed cold or cool gas in the circumgalactic medium. They're thought to be very important for the growth of angular momentum and the dynamical structures of galaxies at high redshift. But all this really relies on the assumption that the cold streams really remain intact all the way toward the central galaxy. And that's not at all obvious that that's the case. And indeed, a lot of cosmological simulations show that as these streams approach kind of about half the virial radius or so, in many cases they tend to break up, or they tend to mix with the hot gas, or they tend to destroy themselves due to thermal instabilities, hydro instabilities, shocks and collisions, etc. However, it's really not, a cosmological simulation is really not the correct tool to study these processes, because even the best cosmological simulations that are currently on the market really only resolve streams near the virial radius by maybe 20 or 30 cells, which is really not enough to resolve the detailed physics that go into all these instabilities. And as a result, different cosmological simulations have provided qualitatively different answers as to the question of how much cold gas actually makes it to the center of the halo, and what its both thermal and dynamical state are. And as a result of that, several years ago, my collaborators and I set forth on a mission to really study the detailed physics of the processes of the interaction between cold accretion streams and the hot circumgalactic medium in a systematic way, using a sequence of more and more complex idealized analytical models and idealized numerical experiments. So to kind of set up the toy problem, you have a hot halo, which is a temperature comparable to the virial temperature. Let's assume it's a few million degrees Kelvin, and a cold stream accreting toward the central galactic disk, which has a temperature of a few times 10 to the 4 Kelvin. If you assume that the stream and the halo are in approximate pressure equilibrium, that implies a density contrast of order 100, or between 30 to 300 between the stream and the background. The second important dimensionless number that defines the problem would be the Mach number of the stream with respect to the background. Now, since the stream is expected to be inflowing at approximately the virial velocity, which is comparable to the sound speed in the hot CGM, you get a Mach number defined as the ratio of stream velocity to the background sound speed of order unity. And kind of the third important dimensionless number that will define this problem is the ratio of the stream radius to the virial radius, which you can show to be of order a few percent to 10%. And to show kind of more systematically how these properties vary as a function of halo mass and like redshift, I'm showing here on the left the density contrast between the stream and the background, which again, what goes into here is assuming that the halo is approximately the virial temperature, the stream is at approximately 10 to the 4 Kelvin, and you have approximate pressure equilibrium between the two. In the center here, I'm showing the actual physical stream density as it enters the halo at the virial radius. This will be important for when I include cooling into the discussion in a few slides. And once you know the density contrast and you have an approximate model for what the density of the hot CGM should be at RVR, it's very easy to derive the stream density. And this is, again, the stream radius divided by the virial radius, which depends on the stream density, the assumption that the stream velocity is of order the virial velocity, and what we know the accretion rate onto the halo to be from cosmology, and what fraction of that would be along a given stream. And just for example, if we were to look at a halo mass of 3 times 10 to the 12 solar masses at redshift 2, this kind of like model would predict a density contrast of order 200, stream density of order 10 to the minus 2 hydrogen atoms per cubic centimeter at the virial radius, and the stream radius of order 10% of the virial radius. Now, taking all these parameters, the first thing you can do is just a linear stability analysis of the Kelvin-Helmholtz instability without cooling, without gravity, just pure hydrodynamics. And what you find is that as a function of the density contrast, the Mach number, and the stream radius over the virial radius, you get that KHI is highly nonlinear. In other words, the number of E-foldings within a virial time ranges from a few tens to a few hundreds throughout the parameter space that we expect to be inhabited by these cold streams. This implies that a linear analysis is really not enough. You really need a nonlinear analysis of these instabilities. And in fact, you can quantify that analytically. You can talk about what is the finite time for Kelvin-Helmholtz instability to completely and utterly annihilate the stream and completely mix it in with the background. That's very different than the linear growth rate. You can do this separately for kind of subsonic flows or more supersonic flows. I don't have time to go into too many of the details here, but the point is that in basically both of these cases, unsurprisingly, the total disruption time will scale as a stream crossing time. It's much shorter the narrower the stream actually is. And that allows you to define in the same space of density contrast versus the Mach number, the largest stream radius in units of the virial radius that will be completely disrupted and completely mixed into the background in less than a virial crossing time. And the upshot is that, okay, depending exactly where you are in this parameter space, but effectively any stream that has a radius smaller than 5% of the virial radius could be completely destroyed and completely mixed in with a hot gas due to Kelvin-Helmholtz instabilities in less than a virial crossing times. Streams that are larger are expected to survive these types of instabilities, and streams that are, the narrower you are, the faster you will disrupt. However, I haven't yet included cooling, which is obviously a very important part to the story. When you include cooling, you have to consider a fourth dimensionless parameter, which is basically the ratio of the cooling time in the turbulent mixing layer that forms at the interface between the stream and the CGM as a result of the shear flows. The ratio of the cooling time in that region to that complete and total stream disruption time in the absence of cooling that I showed on the previous slide. Now, since that disruption time scales with the radius of the stream and the cooling time does not, you can translate this ratio of time scales to a ratio of stream radius to a critical stream radius, which you can basically like write out like this. And if you plot this R stream divided by R stream crit, again, as a function of halo mass and redshift, you learn that for the majority of the expected parameter space, streams are expected to be larger than this critical radius, which implies that cooling is going to be very important and can act to stabilize the stream. How does that stabilization work? These are results of simulations run on the left without cooling and on the right with cooling in that regime of strong cooling, where the cooling time is short compared to the disruption time. And the color here is just a passive scalar that traces the mixing of the two fluids. If you look on the left in the no cooling simulation, you can see that as the instability evolves, the stream seems to throw out material out into the background. You have a lot of stream, initially stream material at very large distances from the background. That dilutes the density of the stream, but it leaves the core of the stream pretty unmixed, which is why you still have the very white color here at the center of the stream. But in the simulation with cooling, you try to start throwing material out into the background, but the cooling time of that mixed material is extremely short. So it condenses and it cools back onto the stream, effectively entraining additional mass from the hot CGM from the background onto the cold stream. That keeps the stream a lot narrower. It prevents you from distributing stream material too far away from the initial spine of the filament, and it very efficiently will mix the hot CGM and the stream, which is why you see this very mixed regime at the end. Thanks for the 2 minutes. Incidentally, if I slightly change the parameters of the simulation to put me in a regime where the cooling time is long compared to the disruption time, you can see that it really closely resembles the simulation with no cooling at all. This is the same thing, but now showing a map of the density, just to make the point that without cooling, the density becomes very diluted, but with cooling, the density stays very high. Now, this process of mass entrainment from the hot component onto the cold component can be modeled in an analytic way. And this is just to show that you can increase the cold mass in the stream by a factor of a few in less than the virial crossing time, and that we know how to model the mass entrainment rate. And once you can model the mass entrainment rate, that mass entrainment leads to a deceleration of the stream, a dissipation of kinetic energy from the stream, and a dissipation of thermal energy from the background as it cools. And that's all these processes can be modeled analytically, and that's what's shown here on the left. It's analytical accounting for all the different energy dissipation rates. And here on the right, I show what simulations produce as the actual cooling rate, just based on local densities and temperatures and the cooling functions. And the fact that both of these plots really match each other quite well means that we can basically model the total emissivity as a result of this process. And it turns out that most of that emissivity comes from that thin turbulent mixing layer around the stream with a temperature just above 10 to the 4 Kelvin, and about half of it is expected to be emitted in the Lyman alpha. And why is that important? Because if I now build a slightly more sophisticated model where I account for the halo potential, and this is the final point that I'll make, as you account for the halo potential and try and again put this in the context of cosmology, I will just say that we have a prediction that the total amount of Lyman alpha luminosity that can be released purely as a result of the stream CGM interaction can be of order a few times 10 to the 43 ergs per second, which is spatially consistent, at least with some of the lower luminosity Lyman alpha blobs that we see out there. I don't have time to talk about self-gravity other than to say that streams are expected to be self-gravitating and be able to form stars. And I wanted to throw up this slide from Jake Bennett's simulation. We heard from him earlier in the week, and other simulations by me that shows that these streams can actually form stars as a result of gravitational instabilities, as well as the thermal instabilities that we talked about. And this can be quite interesting. I'll just skip to my summary and say that massive star-forming galaxies at high redshift are fed by cold streams from the cosmic web. For pure hydro, sufficiently narrow streams completely disrupting the CGM by KHI, but cooling, self-gravity, and MHD basically lengthen the lifetimes of streams. Cooling leads to mass entrainment plus mixing, which might be consistent with Lyman alpha blobs. Self-gravity actually can induce star formation in the streams outside of dark matter halos, and may induce formation of metal pore globular clusters in the CGM and the intracluster medium. And kind of ongoing work is to include more physical processes, combine all these together, account for the turbulence in the CGM, and interaction with outflows and black hole feedback, which is obviously going to be very important. Thank you very much. Sorry for going over.